So we finally built up enough skills to be able to talk about matrix inverses. And what I want to do is kind of start with a different idea, going back to just real numbers. So with any real number, we have something that's called the identity property. And this is if you take a real number and you times it by 1, you always get exactly that number back. And if you do the multiplication in the other way, 1 times A results in A. So 1 is called the identity for this real number system. So this holds for any real number A. Okay. So if I now extend this idea to matrices, what we would need is I need A times something. I'm going to call it I for identity. It needs to equal A. But also if I multiply on the other side, it's got to result in just getting A back. Okay? So in order to be able to move I to either side, the dimensions are going to have to work out. That is only going to work with square matrices. So square matrices are the only ones that are going to have what's called an identity matrix. Okay. So when I times it by I on either side, I get exactly that back. So the n by n identity matrix is denoted with I sub n. It's got n rows, n columns. And the way we define this is you have ones along that diagonal, and then you have zeros everywhere else. So this would all be zeros, and you go down. Then my 2, 2 spot is a 1, and everything else above and below it is a 0. My 3, 3 spot is a 1, everything above and below it is a 0. And then that pattern keeps happening until you get to the NN spot, which is a 1. Okay. So to give you just some mini examples, because we've mostly been working with 2 equations and 2 unknowns. If I look at I2, that's a 2 by 2 matrix, 1s along the diagonal, 0s everywhere else. And I3 would be a 3 by 3 matrix with 1s along the diagonal and 0s everywhere else. Okay? So to show you that if I multiply a matrix on either side by IN, you get exactly the same back. We're going to do this with a 2 by 2 matrix. Given A has the elements 4, 2, negative 7, and 5, we're going to show that when we multiply it on either side by I2, we get the matrix A back. So this is going to require matrix multiplication. So I'll start by doing I2 times A. So I2 has 1s along the diagonal, 0s everywhere else. And we are going to times this by 4, 2, negative 7, 5. So again, this is a 2 by 2 matrix. We are multiplying it by a 2 by 2 matrix. The result is a 2 by 2 matrix because those inner dimensions match up and you get the outer. Okay. So to start, to find this first spot, I'm going to take my first row and times it by my first column. So that would be 1 times 4 plus 0 times negative 7. Okay. And so I'll kind of do both of this simultaneously. I'm going to need a lot more room for the next one as well. That gives us 4 plus 0. So that gives me 4, which is great. That should be my first element. Now I'm going to go ahead and find what's in the second spot here. So in that case, it is my first row, second column. So we multiply those together. So that gives us 1 times 2 plus 0 times 5. And the result of that is just a 2, which is exactly what I want. Okay. And then to move on, this would be the second row, first column. So we go ahead and use the second row, the first column. So that gives us 0 times 4 plus 1 times -7, resulting in -7. So that would disappear. So also works out. And then last but not least, this is the 2, 2 spot. So I use the second row, second column. So we get 0 times 2 and 1 times 5, resulting in 5. So that is exactly the matrix A. If I multiply on the other side, let's make sure that also adds up. So A is 4, 2, -7, 5. And then we're going to times that by I2, which is 1, 1, 0, 0. And again, the result of this is still going to be a 2 by 2 matrix. So that's the only way I'm going to be able to switch the order, is if they both have the same square dimension. So starting with my first element in the first row, first column, I use the first row, first column. And remember, we go again down the line. So 4 times 1, 2 times 0. And the result of that is going to be exactly 4, which is what we want. And then moving on to first row, second column, we use the first row and the second column. So we get 4 times 0 plus 2 times 1. And that indeed gives us 2. This is second row, first column. So we go ahead and we use the second row and the first column. So that's -7 times 1 and 5 times 0. Resulting in -7. And then finally, in our last spot, that is the second row, second column. So we get -7 times 0, 5 times 1. Resulting in +5. So exactly the same thing back, okay? This idea leads into a concept of art inverse. So real numbers have a multiplicative inverse, which is how you get back to that identity number. So if I take a real number and I times it by its reciprocal, that lands me back at the identity, assuming that this number is non-zero. That's the only one that doesn't have a multiplicative inverse, okay? So we have the same idea with matrices. We have a multiplicative inverse, which gets you back to that identity number, or in this case, the identity matrix. So if A is an n by n matrix, then its multiplicative inverse which is written as a to the -1, because this is really a to the -1. It must satisfy the following. If I take a and I times it by its inverse, it better land me back at my identity. So just the identity of whatever order that matrix is. But it also needs to happen for the reverse. If I do the other multiplication, again, I still should end up back at the identity. So just like with the real numbers, this works as long as the value of A isn't 0. For us, we're going to have an inverse, or an inverse is going to exist when the determinant of this matrix does not equal 0. Okay. All right, so let's do an example, and we're going to determine whether two matrices are inverses of each other, and then I'll go ahead and show you how to find the inverse of a matrix. So let's try this example. We're going to see if these are inverses. So again, I want to multiply them in both directions, and I want to see, do I end up with the identity? So let's start our multiplication just in the order that we're given. So we've got 5, 2, 7, 3. And I want to times this by my other matrix, which is 3, -2, -7, 5. The result is going to be a 2 by 2 matrix, because again, they are all 2 by 2. So starting with our first row, first column, we go ahead and multiply these together. That gives me 5 times 3 when I do the first pieces. And then I add doing the next, which is 7 times -2. Okay. Then for my next spot, I again still use the first row, but now I use the second column. So we get 5 times -7. And then we have 7 times 5. Okay. Then moving on to the second row, we have second row, first column. So we got 2 times 3 in that first spot. And then we have 3 times -2. And last but not least, second row, second column. So we have 2 and -7 in the first of each of those. And then we have 3 times 5 being added. Okay. So now doing that algebra, 5 times 3 gives us 15 minus 14. So we'll go ahead and just simplify that immediately. That is definitely 1, which is great. Then here, that's -35 plus 35. So my next element is 0. Then 2 times 3 is 6. 3 times -2 is -6, so we get 0. And then this one is -14 plus 15. So we indeed end up with 1. So this is looking great. This multiplication did result in an identity matrix of order 2. But again, I need to make sure the order works for both. So I have to switch the order that we multiply these in. So instead, we're going to do 3, -2, -7, 5, multiplied by 5, 7, 2, 3. And again, the result is going to be a 2 by 2 matrix. So starting out, we have first row, first column, 3 times 5 plus -7 times 2. Then we use first row, second column. So going down that line, 3 times 7 plus 7 times -3. Moving on to our second row, first column, -2 times 5 plus 5 times 2. And then finally, second row, second column. So -2 times 7 plus 5 times 3. So doing that multiplication, that is 15 minus 14, which is definitely 1. Then we've got 21 minus 21, which is definitely 0. Then negative 10 plus 10 gives us 0. Negative 14 plus 15 gives us 1. So indeed, this resulted in the identity matrix on both multiplications. So these are inverses. If one of them does not result in the identity matrix, then they are not inverses of each other, okay? Now let's try to figure out, if I just give you a matrix, how can I figure out what is its inverse? And so this is going to require those row operations that we might not necessarily love, but we've got to utilize, okay? So finding an inverse, if the inverse exists for a matrix A of size n by n, we're going to go through the following. Again, the way to check if an inverse exists, you need to make sure the determinant is non-zero. So the very first thing you're going to do is you are going to form the augmented matrix where we put A on one side and then the identity matrix of the same size on the other, okay? You are going to do row operations on this matrix A to make it so that it's the identity. So we perform row operations on this augmented matrix to get the left-hand side to be the identity, okay? So we're turning this one into the identity. But you're doing those row operations on the identity matrix simultaneously, so you'll end up with something else on the other side. So essentially, the identity matrix is exactly that row echelon, the reduced row echelon form that we used for solving a system. So you can think of it that way as well. You're just doing those operations to both matrices simultaneously. Once you do get the identity matrix on the left-hand side, the thing that is on the right is exactly your inverse. So matrix B is the inverse of A, okay? So let's try this with a 2 by 2 matrix because again, it extends to a 3 by 3. It's just more operations that you have to do. And we're gonna do this with the matrix 5, 7, 2, 3, which if you go back up here, that's exactly this matrix. So the inverse should be the remaining one we haven't used yet. So this just comes from the last example to show you amazing. This is going to work out, okay? So the very first thing I do is I form that augmented matrix where I put A and then I put the identity of the same size, which in this case is a 2 by 2 matrix. So on the left-hand side, we have the elements 5, 7, 2, 3. And then on the right-hand side, we have a 2 by 2 matrix with 1s on the diagonal, 0s everywhere else. Now I want to get this side to be the identity. So my second step is to use row operations to turn A into I2. And unfortunately, fractions are going to be involved. So gonna have to deal with it and combat it as best as we can. So same thing, you can go ahead and you can swap stuff around if you want. Like if you want to move this into the first spot, to divide by 2, you can, but I do need a 1 in this first position. So I'm going to go ahead and I'm going to take the first row and I'm going to divide it by 5 to get my new first row. Okay. And then I'm going to put these off to the side because we have lots of operations that we need to do. So if I do that, that gives me 1 7/5, 1/5, and 0. And then the second row is untouched. Okay. Then once I get that first position, a 1, then I want to turn everything underneath to zeros. Okay. So for this, I'm going to take -2 times row 1, add it to row 2, and this is my new row 2. So again, going to do all those operations on the side. We've got -2 row 1 plus row 2, and this is going to become our new row 2. So if I multiply this top row by -2, that's going to give me -2, -14/5. Then I have my bar in the middle. Then we've got -2/5, 0. And then we're doing nothing with this row. So when I add them together, that gives me 0. Well, if I want to do -14/5 plus 3, 3 is 15/5. So -14/5 leaves me with 1/5. And then that's -2/5 and 1. So that gives us the same first row. And now my new second row is 0, 1/5, -2/5, 1. Okay. Then the next thing I want to do is I want to get a 1 in that next diagonal spot. So this one's a little bit nicer. We're going to go ahead and do 5 times row 2, and that is our new row 2. So these are untouched. But now 5 times this row leaves me with 0, 1, -2, and 5. Okay. Then I need to get this to be a 0. You can see the fractions are not pretty. I've got to do -7/5 row 2 added to row 1 becomes my new row 1. Okay. So putting all that down, we're going to do -7/5 row 2, right, row 1 right underneath that, and that becomes our new row 1. So I'm just going to copy row 1 to begin with, 1 7/5, then we have our bar, 1/5, and 0. Now I got to times this by -7/5. So thankfully this times -7/5 is still a 0. That times -7/5 is -7/5. This times -7, this times -7, oh, can't type, there we go. -7/5 becomes +14/5. And then this times -7/5, thankfully the 5 and 5 cancel, and just give us -7. So adding these together gives us 1, gives us 0. Here you end up with 15/5, which is nice because that is just 3. So the result for new row 1 would be 1, 0, 3, -7. and then the second row has stayed unchanged. Okay. So this is what I want. I now have the identity matrix on the left-hand side. That tells me what I see on the right is my inverse. So ultimately, A inverse contains the elements 3, -7, -2, and 5. And if I go back up, that is exactly the matrix that I was given, and I know those two are inverses of each other. So this does work out. This is right. This is exactly the inverse we were given. So again, it just comes to utilizing your row operations and putting your left-hand side in reduced row echelon form. So the same exact idea extends if you have a matrix that is 3 by 3, okay? What we're gonna do now, I'm gonna kind of keep utilizing the same example because I don't want this video to be an hour long, because it could be. If you need more examples, there's plenty of other videos out there to show you how to find the inverse. But we want to talk about now, how can we find a solution to a matrix equation? And this is exactly where those augmented matrices come into play. We really can get our solutions using inverses instead. So suppose that A is an n by n matrix with inverse A inverse. X is an n by 1 matrix of variables, and B is an n by 1 matrix. Then the idea is, if I'm taking some coefficient matrix and I'm timesing it by a matrix of variables, and it equals a constant, this is going to have solution where my variables are equal to A inverse times B, okay? So why is this the case? Well, it really just boils down to inverses. Since AX equals B, what I'm going to do is I'm going to multiply this equation by the inverse of A. And remember, the order does matter. So I'm multiplying by on the left. So this is A inverse A times X, and then A inverse times B. Well, when I take a matrix and I times it by its inverse, the result is the identity matrix. And the identity times anything is just X. It's itself. Okay? So what we're going to be able to do, if we have a system of linear equations, we can manipulate it in this matrix form. A is exactly that coefficient of all the different variables. X is just going to be a column matrix of the variables. And then this is the constants on the other side, okay? So let's go ahead and we'll solve the system using the inverse of the coefficient matrix. You can see I picked this for a reason because 5, 7, 2, 3 is exactly the matrix we just found the inverse of. But to show you, this can be written as the following matrix equation. So I have those coefficients. My X coefficients are 5 and 2. My Y coefficients are 7 and 3. We can times this by those variables X and Y. So remember, if I multiply, I would do 5 times X plus 7 times Y. So that's exactly the first equation. Then 2 times X and 3 times Y gives you the second equation. And then that's equal to this matrix with 2 rows and 1 column. Okay. So this is matrix A. This is that matrix of variables. And then on this side, that is the value of B. So it's just a matrix of numbers. Okay. So I already know what A inverse is. So from the prior example, A inverse is the matrix 3, -7, -2, 5. Okay. So my solution to the system is just going to be my inverse multiplied by this matrix, which is my answer matrix. So the solution to the system is A inverse times B. Okay. So we just need to do this matrix multiplication. A inverse is 3, -2, -7, 5. And then B is 4, -1. So this is a 2 by 2 matrix. This is a 2 by 1. So the result is going to be a 2 by 1. So to figure out what that is, again, we go through matrix multiplication. So I take first row, times it by the first column. Going down the line, that would be 3 and 4 being multiplied, and -7 and -1. Then I do the same thing. I have my second row, first column. So multiplying those together is -2 and 4, and 5 and -1. So simplifying that gives us in the top 12 plus 7, and here is -8 minus 5, giving us 19 and -13. Okay. So this is exactly what that solution is. So immediately I can say this is X. So my X and Y are equal to 19 and -13. These are the solutions to that system. Okay. And then again, just to show you that I'm not being inaccurate with this, let's go ahead and solve the system as we would without using matrices. So we can solve the system using elimination too. So our system that we started with was 5x plus 7y equals 4, and 2x plus 3y equals -1. Well, substitution's definitely not easy. Let's go ahead and eliminate the x. So I can get them both to be a 10 by multiplying by 2 and 5. One has to be positive, one has to be negative. So let's do negative on the bottom. The top equation multiplied by 2 gives us 10x plus 14y equals 8. Then the bottom is -10x minus 15y equals 5. So going through, adding those together, the x's cancel. 14y minus 15y gives us -y. 8 and 5 is 13. So look at that, I get y equals -13. Exactly what I got from using matrices. And then I need to solve for x, so I'll just use that first equation. 5x plus 7y needs to equal 4. So 5x plus 7 times negative 13 needs to equal 4. Well, 7 times negative 13 is minus 91. So adding the 91 over gives us 5x equals 95. And then dividing through by 5 gives us x equals 19. So exactly the same answer, just done in a different way. Again, for 2x2 systems, using elimination and substitution is definitely the way to go. It is the simplest method we have. It's very clean and very fast. Because going through and having to find the inverse and then multiply matrices, that is a lot, okay? So I totally get it might seem kind of silly that we go about this, but however, if you're dealing with higher order systems, you have 10 equations and 10 unknowns, that you can't do using elimination or substitution. So a matrix is a much cleaner way to keep track of everything. And this method is actually what computer softwares are doing when you're going through and solving for a system. It is the fastest algorithmically, it takes the least amount of steps. So all of the softwares online are going through and finding the inverse and then multiplying the two together. It is our quickest approach for high order systems. So again, by hand, it might seem really tedious to go through and do, but it is very important for us because it is fundamental in any computer system. This whole branches of linear algebra, okay?